Welcome back, folks, to Restoring Darkness. On today's show, Mark and I are pleased to be joined by Larry Boxler. Larry is an optical engineer with over 30 years of experience involving the development, manufacture, and testing slash validating of optical systems with an emphasis on applications in lighting and illumination and non-imaging optical systems. He has a personal interest in applying optical design to positively impact lighting quality and to help preserve nighttime environments while still providing the necessary illumination for the task under consideration. I think that's very apropos with our show, Mark. At this point in time, we've reached that point. Larry's social, he's on LinkedIn. His social media handle is in the description of the show. I'm very excited to speak to Larry, Mark, but before we do, we got to go. What's up with the Soft Lights Foundation? We need to get that Soft Lights update. What do you got cooking?
Oh, Michael, I'm a little bit exhausted this morning. Yesterday, we had a hearing for our lawsuit, or my lawsuit, against for involving the San Francisco Bay Bridge and the project called Bay Lights 360.
Mm-hmm.
I have filed a lawsuit using the California Environmental Quality Act. The plan was to install 48,000 blue rich LEDs onto the Bay Bridge in a 1.8 mile span, and these LEDs will be animated. I've been asking them about this project and the impact on the environment and human health for a couple of years. They've been brushing me off, so I filed a lawsuit. Yesterday was what was called a demurrer hearing. In California, the government agencies try to get the lawsuit dismissed, claiming that basically the main thing here was that I didn't file my lawsuit in time, that there are these statutes of limitations, so that if they make a decision to do a project such as this, I have a very limited time to file. It was a 3-hour hearing, and I got my chance to tell the judge about how the light pollution will impact everybody, and that it's very new research came out just in April showing about light pollution being bad, and that these agencies didn't comply with the law and do what's called an environmental impact report. And at the end of the 3 hours, the judge said, well, I can feel for you, but you missed your deadline. And so you lose the case. That was pretty devastating. Afterwards, I met with my consultant on the phone, who's helping me. He's also a friend of mine. And we talked about it. And we believe that the judge made a mistake. So the silver lining is that the judge is going to allow us to file an appeal. And in our appeal, we have already looked up case law that when they file what's called a notice of exemption, that they're not allowed to lie. You can't put materially false information on the notice of exemption and say, well, we don't think that this is going to affect anybody, so we're just going to move forward. And then we're filing this piece of paper. That notice of exemption needs to be materially true facts. So we plan on appealing. So my mood has swung from last night from very, very low to now up, and so it's a little bit tiring.
So last night, Mark Baker had his head on his bar with a bottle of whiskey half empty beside him. And this morning, he's back. He's back. You know what? I'll tell you this. Dismantling these types of attrition strategies in the courts can be very difficult, Mark. So what you're up against is a situation where the state or the city or whoever there knows how the system works and deliberately engineers the way they do things in order to set up complainants having cases thrown out at the end. And this is a strategy with non-response to you, perhaps, to delay, not responding to you quickly, not giving you the right information you ask for. And then by the time all that time has gone on and you have all the information now and you file your lawsuit, sorry, buddy, you missed your chance, right? And so these types of attrition strategies are all over the place. Especially with the deep state. And that's the tongue-in-cheek deep state, not the military-industrial complex, but just these types of systems where people are protecting their interests themselves, their pocketbooks, or whatever. They need to be dismantled, and Mark Baker is the superstar of that in the night preservation world. Larry Boxler, welcome to Restoring Darkness.
Thank you. Thank you. It's good to be
So,
on. Not
yeah, it's good to have you. Optical engineer. Describe what that is for me, so the audience listening knows what an optical engineer does.
sure. So essentially, it's kind of like what it sounds. Is we take optical science and apply it to practical devices. So in my case, I have a degree in optical engineering. So that that included the study of reflectors, lenses, lasers, coatings, anything related to manipulating light, for example. And then as an engineer in that field, the I've concentrated my expertise on devices that are generally geared towards illumination or what we call non-imaging, meaning we're not doing something like a telescope or a imaging system. We're doing distributing light um, without regard for image quality. It's kind of a formal definition of what somebody like me would do.
And so you're designing light fixtures.
Yeah, so I would do the upfront design for a fixture. So if you needed to distribute light into a pattern to satisfy a specification or something like that, then I can prescribe the optics that would make that happen.
And in the age of LED, has your profession become obsolete, or has it become more important than ever?
I think it's. I mean, it's uh, there's. I wouldn't say obsolete for sure, and the need for optical design I think has increased over time. As devices have gotten more and more complicated, LEDs have certainly opened up some avenues for different approaches to designing devices, different applications that have opened up for that. But the traditional sources that people think of, the halogens or incandescents or arc sources, those types of sources, typically also needed optical design to for creating the beam patterns that come out of the fixtures.
Now, and I want you to correct me if I'm wrong because I want to totally understand what it is that you do. Okay. So,
Sure.
and I'm going to do that by asking you a question. In the age of halogen, incandescent, LED, fluorescent, not LED, sorry, HID and fluorescent, optics went behind the light source, and in front of the light source might be some kind of diffuser, but the diffuser wasn't really the optics. The optics were behind the light source. And then in the age of LED, what you're seeing is the optic is in front of the light source. So is that correct? Do I have that understanding correct?
It could be both. So if you take, for example, the early in my career, I did halogen based design. So the the basic system would be to have a reflector to collect the light, and then the lens could be used to distribute the light into the pattern. So you could have the if you want to get specific, like a parabola will take a source and focus it into a spot beam, and then if you want to widen it out once it's been focused, then you would put elements on the lens to spread that out. So that's one approach that you can take, and it really depends on what the source radiation is as to what what type of optical system you want to put into there to match it up to the requirements. So it can be both. But your point about a incandescent source, for example, or a halogen source, because it's emitting into a sphere, you're going to have to collect from behind as well to get as much efficiency as you can out of that.
So, but with LEDs, you don't have that collection, right? And my instinct, I don't know if you know the answer to this. My instinct is that that collection of light at the back, or that reflectiveness of light, or that mixing of light on a reflector and redirecting it, fundamentally changes the how that light is seen by humans or how it affects humans. And one of the problems I see with LEDs is that there is no mixing, there's no collecting. It's a directional light source, and its optics are always seem to appear in front of it, and there's this lack of collection or mixing, and this changes drastically the way that light comes out of the and how and what kind of how that light is made up of. It's more directional and glary and those types of descriptions. Do I have that accurately, or am I wrong about that?
It can be that way, but it doesn't have to be that way. Again, it
But it
depends
is
on
that way primarily now.
the so with the LEDs, if you're emitting into a half sphere, we'll call it that,
Mm-hmm.
as opposed to a source that's emitting into the whole sphere, then you're not having to collect the light that's going, backwards away from the target you're trying to light. So you have that advantage up front that the light is coming out forward in the direction that you want it to go to begin with. And then the optical system is placed on top of that to redistribute the light. You can just as easily put it into a reflector first. So, for example, if you wanted to, you could point the LED backwards if you wanted and put it into a reflector and use a lens element on the front. It wouldn't be necessarily an efficient way to do that, but it could be done that way. There's no there's no hard limit on the type of optical system that you'd have to use. It just happens that depending on what your requirements are and what you're trying to do with it, that the LEDs already pointing just in one direction can be more efficient for certain applications. So,
I agree with you that if efficiency were the only metric that mattered, you would never do indirect LEDs. And I think we're
sure.
coming out of an era where the only metric that mattered, Larry, was energy efficiency. And so unwillingly and unwittingly, the lighting industry pointed high radiance, high powered light sources at people. And I think this is causing problems. Do you agree with that?
Sure. So there's a um, the notion that if you have a high radiance source and a small output, that you're going to have essentially high luminance, which can lead to discomfort, glare, and depending on the levels, it can be debilitating. So uh, that's a consideration. If you're putting together a fixture design as to whether or not you have direct view of the optics, that can be something that needs to be considered in addition to uh, the metrics that you're trying to reach for the application itself. Um,
Do you agree that most outdoor light fixtures that have been deployed in the last, I don't know, 10 years, 12 years, are just that? These types of high radiance or luminance, I don't know what the technical terms, but that are causing discomfort, glare, and maybe more, Larry?
yeah, I think a lot of the designs that have been done, they include those kind of optics where you have I wouldn't say direct view of the LED, but the optic is placed over the LED, and the luminance can be quite high along the individual optics themselves. Um, so those do exist, yes.
And do you think this is a problem?
I think it's something that we probably should take a look at if there's better ways to do to light systems while taking all of that into account. Um,
Hmm.
so if you're heavily focused on a metric like just say lumens or lux on the ground, and you're not paying attention to how you're delivering that, you can miss other aspects of a lighting system, which include how it appears to people in the light field, etc.
Larry's put that very professionally, Mark, but I think what I would contend is that when you do that, you cause health problems for people, Mark Baker, with light.
Well, we do know from the Soft Lights Foundation that many people have reported adverse health effects from LEDs, including seizures, a lot of migraine reports, and the blue rich light has caused people to consider suicide. Um, but it's great to have Larry on the show because we want to get into some of these technical details. And Larry, if I could ask you about the this comment that the light from an LED was in a half sphere. It's a little bit more subtle than that, and I was wondering if you would agree that the LED chip is a flat surface, and so actually the light is coming out not actually in a half a sphere, but coming out in a Lambertian spread. And so, are you dealing with that Lambertian spread? Do you know what I'm talking about on that? And do you deal with that in your designs?
Sure. So um, that's one of the points I wanted to address when I contacted the show. So the Lambertian, uh, I think there's a little bit of misunderstanding about what that term, what that means, what that applies to. So if I can, if I can spend a few minutes kind of going into how that arises and how that relates. Um, the the strict definition of a Lambertian is that the intensity varies with the cosine of the angle to the surface, essentially. And so if you're straight on, the intensity is at we'll call it a 1, and then it reduces down by the uh, um, by the cosine of the angle. And so this is not unique to LEDs. There are other radiators that produce that type of radiation, especially black bodies. So an incandescent filament can actually be modeled well by uh, having Lambertian radiation emitting from that. So the kind of the important point about that is when you're talking about intensity, you're talking about a quantity that is essentially ignoring the source size, because the definition of intensity is flux divided by solid angle. So it doesn't even take into account the source size itself. So that quantity, practically speaking, is only valid when you're far enough away from the source for it to be considered a point source. Uh, and there's ways that you can determine whether or not you're okay with that assumption. But the the modeling software that we use to model the behavior of the optics takes all that into account, and we can account for that. So,
Yes, Larry, I've heard that so many times. Our concern is that there's something missing in the lighting industry in relation to this small size or the luminance radiance or possibly the Lambertian distribution. So we have people, for example, that can be exposed to an LED light. For example, in New York, there's a person who their town put in LED street lights after they had originally had high pressure sodium streetlights. She had no trouble with the high pressure sodiums. But when they put in the LED light, as soon as she stepped out her door and got even a glimpse of the LED light, she would suffer the seizure. So it's we don't believe it's an issue of flicker because it's instantaneous. The research university came out and measured it, and they said, "Oh, we don't detect any flicker." That's typically what might be considered for causing the seizures. So we believe that it's the high luminance, possibly also the spread. And so, can you talk to us about like the density of this light, like how like it's vastly more dense, right? Coming out of this tiny little LED versus, say, a previous, or if it was high pressure sodium. Could you talk to us about how, or even throw some numbers at us if you want?
yeah, sure. So I don't know exact numbers for the high pressure sodium, for example, but the LED luminance is quite high from a from a 1 millimeter chip. For example, so if you take a standard LED, they're typically are around 1 square millimeter chip is what they're manufactured at. So those luminance can approach, I think, 10 to the seventh candela per square meter, which is the units for luminance. Um, but that's not significantly different from, for example, a headlamp filament source. also have extremely high luminances. So the luminance is just the product, the result of the area and the amount of flux that you can get out of that area. So the LEDs are especially good at getting uh, a decent amount of flux out of a small area, whereas the other sources that you mentioned, like the HPS or those types, have relatively large areas that are emitting, whether it's the arc source or that type of emission, but that large area uh, lowers the luminance of that particular source.
So hang on,
And
just like so, like a fluorescent tube has a lower luminance simply because the light output is spread across the entire fluorescent tube, whereas a halogen bulb is burning all that light right out of filament. Do I have that understanding correct?
Yeah, that's true. So I mentioned the headlamp bulbs. So those are specialized filaments for for headlamp applications. So they're a lot smaller than you would find in a like a typical 60 watt bulb that you might put in your house, which you can't buy anymore. But those those filaments are a little bit are configured differently than a specialty lamp like an automotive bulb. So so the automotive bulbs are made to be high luminance on purpose.
right. So back to the streetlights. So we've had guests on the show that have talked about the Cobra head streetlights, and there's this big glass, or maybe it's plastic. I'm not sure, that has bevels on it, and he's got pictures that he's got on his website that show how large the streetlight is. I think to spread out that light, right, to make it softer. Whereas I see the LED street lights now, they have, you can see the small chip, I guess. You can see this flat thing with the each individual, and it creates an array, and it's not diffused anymore. So, do you know by any chance, because I have you on the show here, do you know the luminance of those chips? Because I don't know the answer. I haven't seen the spec. The luminance of those chips that are in an LED streetlight.
I don't know for sure, but the a typical LED, the highest luminances tend to be around 10 to the seventh. I think is somewhere in the ballpark.
So this to me is where there's this. I think it's having an impact on our health. So I'm looking at a computer screen, which I believe is probably around 300 candela per square meter. It's pretty bright, and you're talking about some metric that is 10 to the seventh. That's about 10 million candela per square meter. And so there is there some kind of, like, it seems like it's too bright. If I'm looking at a computer screen that's 300 candela per square meter, and that's sort of pretty bright already, and then the LED streetlights is at 10 million candela per square meter, it seems like that could be causing some kind of health issues.
I don't know. Yeah, I can't speak to the health issues, but um, the if the optics are designed in a way that give you a view of the chip, which they sometimes are, you could see luminances on that order, and I mean it's pretty clear that that is at least discomfort glare. So generally you want to try to avoid putting that in the view of direct view of someone, by mounting it up high, using shielding, those types of techniques, or potentially using diffusers, but that tends to change the beam pattern, which may make it not compliant with the street lighting requirements. So.
Hmm. Yeah.
Yeah, the all the requirements. Interesting. The yeah, it's interesting to look at the requirements and see how often our requirements fail us. Um, it's I've seen it. I've seen the government change, laws in Ontario, and these are requirements, right, in a way. And you watch them create perverse environments where the outcome is the opposite of what you want. Um, and this happens all over the place. Is there a fundamental difference between the light emitted in this manner, where this directional LED manner without, where there's discomfort glare, and other light sources, are they actually two different types of radiation? Are they different? Is there something technically different about them that people are not aware of? Like, I'll tell you right now, the lighting industry doesn't think that there's a difference between LED or halogen light. And where it becomes very interesting to me is when you get into like warm dimming things. Like they're trying to get LEDs to mimic a warm dim, of an incandescent bulb. And they're doing all these technical procedures to make it happen so that the theater lights can be LED and dim like the old halogen lights dimmed slowly and steadily and nicely without flickering. Is there a fundamental difference, Larry, between the light emitted by an LED fixture and other lights or other conventional light sources? Are they totally different from one another?
I mean, I wouldn't say that they're totally different. Uh, it, there's an obvious difference in the spectral content is different, right, between an LED and a halogen. If you're attempting to match a halogen, so that's different. There's no question on that. The behavior of the light it's the same across sources. When we model these systems, the ray tracing software that we're using, we're setting up the same exact um, simulations to whether it's a LED or a halogen. The difference being, the geometry of the source is taken into account in those, but it doesn't. There's no difference happening physically to predict the light output from that. A source is a source in that regard. So the main one of the main differences when you get into LEDs is that they're a semiconductor device, so they can be instantly switched on and off, which is a little bit different behavior than, for example, as you were mentioning, the dimming of a halogen or an incandescent bulb is gonna be a little bit different. You can't instantly dim a halogen, right? So matching your dimming curve up to the way the halogen is acting requires a little bit of, I guess, specialized electronics to make that appear the same. But you can turn an LED off, instantly, and it stops emitting. So there's that kind of digital nature to that, and I think that the flicker research that's come out recently, the LEDs are capable of producing different waveforms of that flicker, and I think people are probably picking up on that. If there's people that are sensitive uh, to the different frequency content that results from that kind of uh, dimming application.
I'm going to throw it over to Mark. What I'm hearing, and I'm not sure if Larry and I agree yet, but I need some more time to think about what he said on the show here, which I think is a totally different perspective, Mark, that we've ever heard before. But what I'm hearing is that, and this is what I believe now, is that different kinds of lights and different types of optical reflectors fundamentally change the electric light in some way, and that sometimes these changes can make us uncomfortable, it can make us sick, it can cause different problems, or it can be great. It can be really wonderful to be under that kind of light. And so different kinds of light create different effects on humans, Mark Baker. That's kind of what I'm learning here, sort of.
Yeah, that was great, Michael. So what Larry's told us has helped us understand, and I think that I could say it also that patterns. So we have spatial patterns and spectral patterns and temporal patterns, and it's super complex. And humans and other creatures have biological life have evolved with certain patterns, like sets from the sun, maybe stars at night, maybe the reflected light from the moon. And now we've introduced this ability to tune our light, to have directionality, to have different spatial distributions, to have higher intensities, to have different spectral distributions and temporal distributions, flicker and pulsing. And you mix them all together, and we don't know out of the trillions of combinations of all of that light which ones are safe and healthy for us and which ones are causing us to have seizures and migraines. I don't think you, I mean, it would be like mapping the human genome. It's, it's giant, the number of permutations of these combinations of the different types of light. And so I think somehow we need to understand which light is safe and which light is not safe. And I don't think we're doing that. Larry, to get back to your comment about, I'm very interested. I have a degree in electrical engineering. I haven't really used it for a long time, but um, I'm very interested in the software that you use to ray trace. And you mentioned that you do actually input the geometry of the source. Could you tell us, our audience and me, so how does that work? How do you tell the software what the geometry looks like?
Sure. So there's a couple of ways that can be done. So I guess one point I want to make is that there's a um, within the lighting industry, there's a couple, I guess, different software tier. We'll call it tiers. Maybe that's I don't want to make anybody mad, but so there's lighting application software, which is what you would use if you were doing a layout for an area, right? So if you had you had to light an area and you needed to show that you were going to meet the requirements or whatever it was, you would pull in the files from the manufacturer, put it into the software, and it would run the calculations and tell you if you were meeting requirements. That's kind of uh, a broad brush of what that software does. And then behind that is what I use is what we would call optical design software. It uses a different approach, which typically is called Monte Carlo ray tracing. People might be familiar with ray tracing from hearing it from gaming graphics and things like that. It's literally kind of what you might think of as we're tracing individual rays through the system and tracking that to be able to keep track of that. So when it comes to modeling the source, if you want to have a really detailed, accurate model because yeah, you're really up close to the source and it matters. You can't just use the intensity file that you would get from the output. You need to have that detailed model. So it literally is just so if I were modeling we'll take the headlamp bulb for example. I would draw the coiled surface to the dimensions that it is using could be using a CAD software, for example, and then that surface would be put into the optical software. And then to be able to simulate the source, then you would launch rays off of that surface and apply the proper distribution for that type of source. So in the case of a incandescent, it would be Lambertian radiation applies well. If you were modeling an arc source, it might not be Lambertian. It might be a little different. But you would need that detailed information, and the software has the ability to take in that information and correctly model that as the rays are being traced through the system. The other way that that's done. Sorry, do you have a question, Mark?
Well, no, you keep going, but I do want to
Okay.
ask you a question at the end. So please keep
Okay.
going.
Sure.
Yeah.
So the other way that it's done is to use what they call I think I don't know if it's common, but it's called a source imaging goniometer, um, and that's a technique where you use a camera to take the pictures of the source in the near field, what's called the near field. So you're up really close to the source, and once you have those luminance pictures, you take it over the entire emission of the source. So if it's a halogen source, you're going to take it over the full sphere that it's emitting into. If it's an LED, it's just going to be the whatever the LED is emitting into. But you can take those pictures, and there's some really smart people that figured out how to turn that into um, files that can be used in the optical software that will replicate that um, source output in a detailed way. So there's kind of two ways you can approach it, and depending on what you're trying to do, you'll use one of those or both in the software.
Wow. So that's great. It really helps me understand. And so that's why I triggered this question that ties into what Michael was talking about just a second ago. So our members, our supporters report to us. I have a website, and for the past year, we've been collecting LED incident reports, people that are suffering harm. And so they report those to us, and then I submit those to the Food and Drug Administration once a month. So we have collected just in that little site over 300 reports of people being harmed I would call it injury from the LED light. And so it feels like, so when you're doing the modeling software, this is how the light comes out. But Michael and you talked about that the rules is how the light then spreads on the sidewalk. Would you agree that we don't really have any rules like for how the light then impacts the human, so that we don't have any modeling software, like, so you have your source and then you have a model of a human and showing that light coming and landing on the human and then figuring out which patterns and at which distances and at which pulse rates and at which spectral contrasts causes them to have a seizure. There's
So
nothing. Go ahead, please.
yeah, so I mean, with the software that we have, we can model that all the way through to the eye if we want to do that. So there with the Monte Carlo ray tracing, there's no limitation to what uh, you can derive from it for the photometry is the term that we use. So we can look at the lux on the surface. We can look at the intensity from the far field, which is what you would need for your IES files that you're going to use in your application software. We can look at the luminance of the scene. We could actually model the human eye as it exists, well, with the properties that we actually have, and look at the irradiance on the retina if we wanted to in the software. So the software is perfectly capable of doing all of that type of analysis. The question is, when do you need to apply that, and how do you use that?
How do you test in the field if your software is accurate?
So typically, uh, you're going to test with a detector of some sort. So in a simple case, if we're designing a fixture for something that we're gonna give to lighting application engineers, the software will predict the intensity output that we would expect to get from the manufactured lamp, and then we would take the manufactured lamp to the what we call the goniometer in the lab, and that's set up to be able to measure intensity, so that we can take the data from the manufactured part and correlate it back to the software. And over time, that capability has gotten better and better. When I first started in the in this 30 plus years ago, the computers were just getting started into it, and so the capabilities evolved over time. But it's to the point where, as long as you have the correct um, optical properties assigned, based on the materials that you're using, you expect that simulation to be accurate to within a few percent of the actual part.
The um, does the lighting industry or manufacturers, do they use this kind of software, or do they hire you, or how does this software how is it utilized in the lighting industry?
It's a combination of both. So the some of the it's a I guess you can imagine it's kind of a niche field, so the not everyone can bring on a full time optical engineer for their doesn't make sense for their business. But some of the larger companies will have optical engineers on staff, and then other people will do contracting as needed during the fixture development.
Well, Larry, did we? I mean, we're coming up on 40 minutes, Mark, if you can believe it. Just like that.
There's so much more. There's so interesting. There's so much more I want to know.
Yeah.
Go ahead, Mike.
I was just going to say though, Larry is, maybe we can have you on again, to kind of let us think about this a little bit and then come back to you maybe with some more intelligent questions. But if you have, did we miss anything that you wanted to say to the audience of Restoring Darknesses, or something that, that's pertinent in your mind that you want this community to know about?
No, I think I appreciate the opportunity to come talk, because we're we usually aren't front and center talking to people, um, and so there's not a lot of, I guess, um, awareness of what's actually happening, behind the scenes when a fixture is being developed, and the kinds of issues that get brought up with relation to lighting, we're aware of those. We can predict it, and we know, and we can mitigate that. It's just a matter of getting to the point where the incentives to make it meet requirements and be, uh, we'll call it human friendly or whatever you want to call it, are part of the entire process.
Hmm. Well, that's been Larry Baker, and it's been another Larry Boxler. Sorry, Boxler. Oh my
Yeah.
goodness. I'm sorry. I'm just sitting here thinking my mind's been blown by our conversation, Larry. It truly has. And my the wheels in my head were just, when you were talking, the wheels in my head were just spinning thinking about how, this people in the lighting industry need to start thinking about what it is you do and why that's important. And and then to expand that knowledge and advance that knowledge and bring the microphone and find voices for other people in the lighting industry that, like you said, usually are not on the stage talking at conferences. If you want to support this kind of work, you can go to restoringdarkness.com. There's a donate box there. You can click the donate link. Hey, I wouldn't say to become a recurring donor, but hey, if you want to help out with the production of this show, you can donate there. You can also donate directly to the Soft Lights Foundation. If the favorite part of this show is the Soft Lights update, like mine is, you can go and click softlights.org and you can donate directly to the Soft Lights Foundation. We also want to thank our friends at the National Association of Innovative Lighting Distributors. That's NAILD.org. And yeah, see you next time on Restoring Darkness.